Hello and welcome to The Explainer. Today, we're basically going to be detectives. We're tackling a classic physics problem from the famous Irodov collection, and our mission is to figure out a particle's mass using just a few clues about its orbit. It's a fantastic example of how a couple of fundamental laws can unlock secrets hidden deep inside the motion of an object.
So, let's start with the big question that's driving this whole thing. If you only know a little bit about a particle's path, like its shape and its speed at just one single point, can you really figure out something as fundamental as its mass? Well, the answer is a big yes, and we are about to see exactly how it's done.
Here's our game plan for cracking this problem. First, we're going to break down the challenge itself, just to make sure we understand all the clues. Then, we'll get our physics toolkit ready. After that, and this is the important part, we'll find the most strategic points in the orbit to focus on. Once we have a solid plan, we'll walk through the solution step by step, and finally, we'll wrap it all up with the key things you need to remember for other problems like this.
All right, first things first, the central force challenge. Before we even think about solving anything, we have got to carefully look at what the problem is telling us and pull out every single piece of information. Let's deconstruct it together. So here it is, problem 1.191. Now, it says the particle is in a closed trajectory. What does that mean? Well, it's just a fancy way of saying it's in a stable orbit. You know, one that repeats itself over and over. The force field is given by this potential energy, U equals kr squared. And our most important clues are its closest distance, which is r1, and its speed, v2, when it's at its farthest point. The goal? Find the mass.
Okay, so let's get organized. On one side, we've got everything we know. The formula for potential energy, the fact that the orbit is stable, and these two very specific measurements at the orbit's extremes. And on the other side, we have our single target, find the mass, m. Now, to solve this, you don't need any obscure, complicated formulas, nope. We just need two of the most powerful and fundamental tools in all of classical mechanics. Seriously, these are the concepts you'll come back to again and again. Tool number one, conservation of mechanical energy. So, because this force is conservative, which basically means no energy is being lost to things like friction, the total energy of our particle is completely locked in. It can trade its kinetic energy, its speed, for potential energy, its position, but their sum, that total energy, E, stays absolutely constant at every single point in its path. And our second tool is the conservation of angular momentum. Now think about this. Since the force is always pointing right toward the center, it can pull the particle in or let it go out, but it can't give it a twist. There's zero torque. And if there's no torque, the particle's angular momentum has to stay perfectly, absolutely constant. Okay, now this is the crucial insight that really unlocks the whole problem. Instead of trying to analyze the entire complicated orbit, our strategy is to zoom in and focus on the two most special points, the closest it gets and the farthest it gets. These special points are called the apsides. Think about it for a second. At the exact moment the particle is at its closest or farthest point, it's not actually moving closer or farther away, right? It's just for an instant. Its motion is purely sideways or tangential. And that is our secret weapon, because when the velocity and the radius are perpendicular to each other, the math for both energy and angular momentum gets so much simpler. Okay, we've got our tools, our strategy is set. It's time to put these laws into action and actually turn these physics concepts into our final answer. Let's do it. So here's our four-step plan. First, we're going to write down the energy equation at both of those special turning points. Second, we'll use the conservation of angular momentum to clean those equations up a bit. Third, we'll combine them to find a really nice expression for the total energy. And finally, we'll use that to solve for the mass. Okay, let's break this down. Don't let the equation scare you. The total energy, E, is just kinetic plus potential. That k r1 squared part, that's just the potential energy. Easy enough. Now that first term, m squared over 2mr1 squared, might look a little weird, but it's just a really clever way of writing the kinetic energy, 1/2 mv squared. Remember how at the turning points the velocity, v, and the radius, r, are perpendicular? Well, that means the angular momentum, m, is just mvr. If you solve that for v and plug it into the kinetic energy formula, you get this super useful version that uses the constant m instead of the changing velocity v. And now for a bit of magic. Since the total energy E is always constant, the energy at the closest point has to be equal to the energy at the farthest point. So we take those two equations from the last slide and set them equal to each other.
We do a little bit of algebra, and after the dust settles, we're left with this incredibly clean and elegant formula for the total energy. It only depends on the distances of those turning points.
But wait, let's not forget the clues the problem gave us. We know the velocity, v2, at the farthest point, r2. So we can also write a second, much more direct expression for the total energy E at that exact spot, just using our standard formula, kinetic plus potential.
And here it is, the checkmate move. This is such a classic physics strategy. We now have two totally different ways of describing the exact same number, the total energy E. On the left, we have the one we figured out from the orbit's geometry. On the right, we have the one using the specific values from the problem. Since E has to equal E, we can just set them equal to each other, and boom, we have the one equation we need to solve for our unknown mass.
And now, we just solve it. It's actually pretty straightforward. You see on that first line, there's a kr2 squared term on both sides of the equation? Well, they just cancel each other out. That leaves us with kr1 squared equals 1/2 mv2 squared. We just rearrange that a little bit to get m by itself, and there's our final answer. M equals 2 kr1 squared over v2 squared. We found the mass, using only the clues we were given. So we did it. We got the answer. But what did we really learn here? Let's take a moment to turn this solution into a strategy you can use again and again, and let's point out some common traps you'll want to avoid when you run into problems like this. So the huge takeaway here isn't just about this one answer. It's about learning a strategy. Whenever you see a central force or an orbit problem, your first thought should be, what's conserved here? Then look for those special points of symmetry, like the apsites, and apply your conservation laws there. And remember that move we pulled, finding two different ways to write the same constant? That is an absolute powerhouse technique in physics. And finally, let's talk about the common mistakes to avoid. The biggest trap, by far, is using the simple F equals mv squared over r formula. That only works for perfect circles. This orbit isn't a circle, so you can't use it. Also, a really simple mistake is just mixing up your variables. Remember, the problem gave you v2 at the farthest point, r2. Make sure you keep them paired up correctly and don't accidentally use v2 with r1. So I'll leave you with a little challenge to think about. What if the potential energy wasn't kr squared? What if it was the one for gravity, U equals negative k over r? The amazing thing is, the fundamental strategy we used today, using conservation laws at the turning points, would still be the key. But how would the math be different? Give it some thought. That's all for this explainer. Thanks for joining me.